Let's roll sound.
Rolling.
And action.
All right, AB students, this is 10-2. We're going to explore some more limits. Okay, let's go to letter A here. And we're still starting to explore limits for the first time ever, so you're still kind of iffy on the instincts, and that's what I'm trying to instill in you. So here we have a finite limit. Obviously, it's not infinite, right? And if you kind of remember, so graphically, if you look at a graph, then the limit is kind of approaching from both sides or from the right or from the left. This is approaching C, but there's no plus or minus, so that does mean from both sides of C, all right? Now, we don't have a graph. We don't know what this graph looks like. The graph is actually way too much effort this time. That's not a graph you're supposed to know. If you just pretend like C is a number, by the way, you can kind of picture it a little bit better. But if you can't graph it, remember we have other methods, algebraic methods. So as a student new to limits, it's probably best to picture the one from last time where we had x squared and we had the limit as x approaches 3 and we said just plug in 3 and see what you get. And we got 9. We actually got an answer, right? Okay, so if you don't know what a graph looks like, take C, just plug it in. That's the very first thing we always do with limits, unless you have a picture, of course. You just look at the picture. So take C, plug it in, see what happens. So see what happens. C minus C on the top would be 0. Okay, that's perfectly fine. The square root of C minus the square root of C, also 0. What did we say? We said that almost every limit you see is going to be 0 over 0. I think I mentioned that last time. That's the indeterminate form, right? Indeterminate form number 1 of 7 that exist in Calc 1, Calc 2. So that tells you nothing. 0 over 0 could equal 57.6. Tells you nothing in math. So it tells you to get out of that form. Now remember last time, we had one that was 0 over 0 in 10-1. And we factored our way out of it. We factored the top and we got a little cancellation going. All right. Well, you can't really factor x minus c. And you can't really factor the square root of x minus the square root of c. So what if factoring is not an option like it was last time? Because that was kind of the theme last time. So when you can't factor, what do you try? All right, let me actually erase this here. It's okay if you have it on your notes, but I want to show you something that I believe you learned in pre-calculus. And it came up loosely like back when I used to teach integrated 2, but it came up with imaginary numbers and not this situation. But from pre-calculus, there's something called a conjugate, all right? You will use the conjugate in limits when this happens. If one term has a square root over it, and then there is a second term that either has or doesn't have a square root. It doesn't matter if the second one has a square root. But if you see a square root plus something or a square root minus something, all right? 2 terms, the first one's a square root of x or the square root of something with an x under it, it's going to be a conjugate problem. Even the crazy, nearly impossible ones they teach you in college, they're all conjugates when there are 2 terms and the first one has a square root on the x. So if you remember from pre-calculus, the conjugate of something with 2 terms is to write the exact same thing but to change the sign in the middle. So the conjugate is going to be the square root of x plus the square root of c. It's the only way out of this mess, all right? Now, you always do the conjugate of the part with the square root. Then you ask yourself, hey, if I do it to the bottom, wouldn't I have to do it to the top to be fair? So then you put the exact same thing on the top, okay? That's not the conjugate of this one. It's just a balance of what you did on the bottom. All right, now we have the limit as x approaches c, and we're going to FOIL. But we're not going to FOIL the numerator because those aren't conjugates. You might have FOILed them actually back in pre-calculus. You only FOIL the part with the conjugates, not the other one, otherwise that'll ruin the surprise. So on the bottom, the square root of x times the square root of x is just an ordinary regular x. We even did that in integrated 3. The square root of x times the square root of c, they can be combined because they have the same root. That would be the square root of cx. But that's the outer. The inner is minus square root of cx. So remember, when you write a conjugate, the outer and inner end up opposites and cancel each other out, and they disappear. And then you do the last, which is negative times a positive is a negative. Square root of c times square root of c is just a regular c. And maybe now you see why we don't FOIL the top. Leave it. X minus c, quantity, and then quantity square root of x plus square root of c. Do you see it? X minus c's cancel, okay? That was triggering the 0 over 0, by the way, because put in c, just right now, put in c for x. Look at that. That's 0, that's normal. So there's your 0 over 0 that was in there. You got to fish it out of the problem and get it out of there. Well, there's your cancellation. It can only be done by conjugates. Now take the limit as x approaches c of the square root of x plus the square root of c. All right, now plug in c for x. You've now escaped the indeterminate form. It can't be 0 over 0. It's not even a fraction anymore. So it couldn't be 0 over 0. Plug in c. You get the square root of c plus the square root of c, which is 2 square root of c. And that is your final answer for the limit. Okay? It's all about your algebraic skills and what you can make happen in a limit problem. Because they'll give you some that you can easily graph. We'll do some today that you can just draw a picture because you know all your pictures. You know your major graphs in my class, right? Some of these, draw a picture, look at it, you can see the limit right in front of you. Some of these you can't graph, so you trust your algebra skills. Because it was a 0 on the bottom, that means the original function doesn't even exist at x equals c, because you can't have 0 on the bottom. That's discontinuity. So the function does not exist, which means vertical asymptote or whole, or disjoint if it's a piecewise function. It could have a jump, but this is not a piecewise function. So this is either a whole or a vertical asymptote there. Well, if you get a limit, if you get an answer, only a whole cannot exist but have the limit from both sides in agreement. And we just got an answer, so that means it agrees from both sides. It's got to be a hole in the graph, okay? So complete side note, but you will use this year. There's a hole on the graph at c comma 2 square root of c, wherever that is. And now you could plug in a number for c and actually get an outcome, but just wanted you to know that on the side, all right? Now let's try letter B. So we have the limit as x approaches 0 of this crazy looking function. Okay, let me go through some of the pointers that I teach my students because it's really the same system every time you do one of these limits. First question I ask myself, could I just easily graph it and get it over with and see the limit? We don't graph those, do we? Nope. Okay, so plan B. Take 0 and plug it in. Just take the thing that it's approaching and plug it in and see if you can get away with it, because sometimes you can. So you take 0, you plug it in. You get the square root of 9, which is 3. You see it happening already? 3 minus 3 is 0. And then you also get a 0 on the bottom. Okay, you see it? 0 over 0. Indeterminate. 0 over 0 could equal pi plus 1. I mean, it literally could equal anything. Indeterminate means you're not telling me very good information. So then you look at it and you think, could I factor from 10-1? That's not a factor problem. Is it a square root of a variable and then plus or minus something else? Yes, that is technically 2 terms. A square root and then a minus, and then the 3 is the second term. That is a conjugate problem, all right? So when you see square roots in high school and college calculus, you're going to do a conjugate unless sometimes you'll see a problem where the square root goes over the entire numerator. That's a different discussion for a different day. If it went over the whole numerator, would that be 2 separate groups? No, wouldn't that be like one big radical? Okay, so you've got to have radical and then plus or minus second group. You can't have just the whole top under a square root. It doesn't work. It's not going to work by this method. So immediately I look at the square root, I see it's 2 terms, I write the conjugate right next to it, which is same square root, don't change the plus 9. Change the minus to a plus 3. That is the conjugate from pre-calculus. And if you do it to the top, you do it to the bottom. So now we put this down here. Okay, now remember our methods with this conjugate, because this conjugate is going to save you on the AP test. It's going to save you in college. You FOIL the conjugates. Square root times itself gives you the radicand. We used to use that word in integrated 3. The radicand is the thing under the radical. Square root times square root is the radicand, just a regular old x plus 9 in its own set of parentheses. Outer, inner, opposites, cancel. Don't even worry about those. And then last. First, outer, inner, last. Negative 3 times 3 is a minus 9. All right? Tempted to distribute the x, we usually distribute, don't do it. The non-conjugates, just leave them alone and write them down. And then you might notice your breakthrough, okay? If you plug in 0 for all the x's right now, you're still going to get 0 over 0. But x plus 9 in parentheses, you actually don't need the parentheses anymore because there's no power on it. There's no coefficient in front of it. We can unlock the fence. There really wasn't a lock on it anyway. So we can just open the gate because somebody left the lock off. So now the dogs are free to run around the neighborhood, and the plus 9 and minus 9 cancel each other, and you just have an x as your numerator. Look, x on top, x on the bottom. The only time you can cross cancel in any math class is when you have multiplication, and that is multiplication right there. You're allowed to cancel the x's, aren't you? Once the 9s depart, the x's can cancel each other, only after you get rid of the 9s. All of the x over x, that's what was causing the 0 over 0. Do you see it? So now our new limit is the limit as x approaches 0. Nothing is left on top. As you all know, though, you're all pros. You have to at least put a 1, right? On the bottom, let's see, that's gone. So it's square root of x plus 9 plus 3. I went ahead and dropped the parentheses because if you're all by yourself, you don't need parentheses anymore because that x is gone. Now that you eliminated the secret 0 over 0, couldn't you plug 0 in for x now, which is the whole way you're supposed to get a limit, is to try to plug it in. You just couldn't, and then you couldn't, and then you can, right? So now you plug in 0. You get the square root of 0 plus 9 with an extra plus 3 on the bottom. Square root of 9 is 3. 3 plus 3 is 6. 1 over 6. Your answer is 1/6. Now, who would have thought that 0 over 0 would equal 1/6? That's why it's called the indeterminate form. You never know. Now, does 0 over 0 really equal 1/6? Not quite. We're approaching 0. In limit world, remember, this is a new world for all of us. In limit world, you are going towards 0. You're getting super close to 0. 0.1, 0.01, 0.0007, tinier numbers. And also from the other side simultaneously, both sides. Negative 0.1, negative 0.01. And the closer you get to 0, the more this thing converges, good math word, to 1/6. Okay? But remember again, isn't that a hole? Because if you get the limit from both sides to be a number, then the final thought of the graph would be there's a hole at 0, 1/6. Another good thing to know. Today we're just doing limits, so you just leave it at 1/6. You're done. All right?
And now it's time for Indeterminate Conversations with Mr. Wade.
Yep, it's that time again. Indeterminate conversations. All right. Let's have some more of those because these are things that every calculus student needs to know. 0 divided by infinity. Let's say you took a test and there were infinite questions on that test. Wow, that's pretty intimidating. And you got 0 out of infinity correct. Wouldn't you get a 0 on the test, right? 0 over anything is 0. Except 0 over 0. Remember, that was indeterminate. So 0 out of infinity questions is 0. And then the test analogy is really good to help you with this. Hey, some other student got 10 questions right out of infinity. Think about that. If you got 10 questions right out of infinity, didn't you pretty much get a 0? 10 is like nothing out of infinity. Infinity is so powerful, right? That's 0. Okay? I mean, I don't care if you get a billion out of infinity. You still got a 0 on the test. Because while you may have gotten 1 billion questions right, you got the other infinite wrong. Think about that, okay? Now, infinity out of 10. Okay, if you take infinity and divide it into 10 sections, isn't that still infinity, right? Because it's so large. So that also gives us an infinity. Okay, all these are determinate. They can all be determined. So then we get to infinity out of infinity. What if you had infinity divided by infinity?
What's the biggest number you can think of?
10.
Okay. How about you?
Infinity.
Can you top that?
Infinity and 1.
Actually, we are looking for infinity plus infinity. Sorry.
What about infinity times infinity?
Ah, classic commercial from your youth, if some of you remember that one. But infinity divided by infinity. You know what? That is also indeterminate. And let me explain the clash of ideas here, okay? When infinity is on the bottom, anything out of infinity is zero, if you noticed. When infinity is on the top, it wants to be gigantic and become infinity. But see, that's a clash of ideas. Infinity on the top, I want to be infinity. Infinity on the bottom, I want to shrink to nothing. Clash. NEI, not enough information, what we formally call indeterminate. And now we're going to call this indeterminate form number 2. All right, this is the second of 7 different indeterminate forms, the second most popular. 0 over 0, easily the most popular. This is number 2. We're only going to do 3 in AB. All right, we're about to do the third one right here, actually. And then we stop there. Calc 2, you can do number 4, 5, 6, and 7, or in BC calculus. Okay, so that's a clash. What about infinity plus infinity? If I had infinite dollars plus infinite dollars, that's infinity. Okay, that's determinate. What if you lost infinity dollars and then you lost infinity more dollars? That's negative infinity. You just lost infinity dollars. Okay? That is perfectly determinate also. Infinity minus $100. Here, I have infinity dollars. I'm an infinity-aire instead of a millionaire. I'm going to give you $100. I still have infinity dollars. Okay? Those are all infinity. Here's the one, though. What if I had infinity and I took away infinity? Some of you might think, wouldn't that be 0? No, there are different degrees of infinity. There are stronger infinities, there are weaker infinities. Who's stronger? I don't know. I don't have a problem to look at here. Okay? Good reference, by the way, because I've talked about these graphs a lot with all of you. You all know that the natural log of x levels off, but eventually doesn't it reach infinity? Eventually? That's a very slow infinity. What about exponential growth? Doesn't that go quickly upward to infinity? Now see, here's the thing about infinity. It's not a number, it's a concept. Both of those things take forever to get to infinity, and they really don't ever get to infinity. They try, but they can't get there. But isn't exponential growth a lot stronger type of infinity than a logarithmic infinity? So see, there's the problem. That is indeterminate. You cannot tell what infinity minus infinity is. It could be 22. So NEI, and we now have indeterminate form number 3. Here we'll just put IND and abbreviate it, number 3, so you don't have to write so much. Okay? So that's the other one to watch out for in this class. Very interesting, all right? Probably should have said this too. If you have like 10 over 100, that's a small number. If you have 10 over 1,000,000, that's a tiny number. If you have 10 out of 1,000,000,000, that's a very small number. And the bigger the denominator grows, the less the fraction is worth. It shrinks to a smaller value. That's why 10 out of infinity is basically nothing. Okay? That's another good way to think about it conceptually. Now let's try letter C. And in preparation of letter C, we're going to draw 4 graphs that you should all know by heart by this point. Even back in integrated 3, you knew all these graphs right here. First one is y equals natural log of x. Can you hear Mr. Wade's voice saying, "Thou shalt know thy graphs," with a big echo on a mountaintop? It's one of Mr. Wade's 10 rules. Okay, we all know the natural log of 1 is 0. 1 comma 0, great anchor point. We all know that you cannot take the natural log of 0, or for that matter, anything negative, only positives. Why can't you take the natural log of 0 graphically? There's a big vertical asymptote right there. And then, of course, the natural log just looks like that. Okay, you will need to have that graph committed to memory, which you all do already anyway. Y equals e to the x, must know it by heart. E to the 0 is obviously 1. So 0 comma 1 is a great anchor point. By the way, natural log of x and e to the x are inverses. And isn't the inverse of 1 comma 0, 0 comma 1? We don't talk about that enough. We did in integrated 3 once, but that is very important, by the way. And as weak as this one rises that quickly because it's the inverse. Of course, you can never get to the x-axis with exponential growth. It goes up, it tries to land, but it never gets to the runway. Everybody knows e to the x, right? Okay, third graph, quickly. y equals e to the negative x. And of course that is exponential decay, but e to the 0 is still 1, isn't it? So you can still trust 0, 1, even for decay. You can still trust there's a horizontal asymptote on the x-axis. The only difference, of course, is it kind of looks like that. All right? And then finally, the last one is 1 over x, which we don't graph quite as often as the other three. But when you see 1 over x, and especially when x is to the odd power, isn't that x to the first? 1 over x to the first is a hyperbola. Remember this one? This was an integrated 3. Let's go over here. You've got a curve, and I didn't even film that. You've got a mirror image. You've got a vertical asymptote. You've got a horizontal asymptote. That's 1 over x. And while we're at it, if it's 1 over x to the third, 1 over x to the fifth, 1 over x to the seventh, anything odd, it's going to be the hyperbola. From the what I call the cigarette smoking chapter of integrated 3, where we used to talk about like inverse relationships with your health and things like that. So now we can go to letter C. We can do these so quickly. I mean, really, really fast. You will have such an easy time with this because I've been preaching these graphs for years, right? And most of you have had me prior and have me now. So, okay, what did we say just a moment ago when we were doing those other problems? Didn't we say first instinct, try to graph it if you can? And if you can, easy. If you can't graph it and see it, try to do some algebra, right? Factoring, conjugates now, I give you a new superpower every day. All right. Natural log of x, e to the x, e to the negative x, 1 over x, the same graphs up here. All graphs you know. When you see a problem like this, you immediately would say to yourself, I already know what the graph looks like. Why would I do anything else other than just draw the picture or even just see it in your head? Most of you can do this just in your head. So we're going to do the infinite limit of all 4 pictures, okay? If I put limit as x approaches infinity of natural log of x on a test, you would immediately picture the natural log graph, and you would think, as x goes to infinity, so as you march down the x-axis to the right forever, positive infinity, where is natural log of x going? It's rising higher and higher and higher. Does it ever get to a ceiling? Nope. It might take until outer space, until you finally cross the top of the board. We've had that whole conversation, right? But the answer is infinity. There is no upper boundary, okay? Simply look at the graph. If anybody in AB right now is thinking, Mr. Wade, is this end behavior that we did in integrated 1, integrated 2, integrated 3? That's why we teach you end behavior for calculus. This is just end behavior. Do you all remember that stuff, right? Maybe you've done it in pre-calculus. You do it every year. It's probably the one thing you do, by the way, every year from integrated 1 to 2 to 3 to pre-calc to calculus. That's like the one constant, it seems, other than just, I guess, graphing in general and maybe y equals mx plus b for the equation of a line, whatever. So, all right, limit as x approaches infinity of e to the x. Picture exponential growth. As x goes to the right forever, the arrow is going up forever. And remember, limit answers are y's always. So the y is going unbounded, no ceiling. It's going to go to infinity. Just knowing your graphs. Now, this is an interesting one. What if I give you, because I will, the limit as x approaches infinity of exponential decay? You picture the graph. You go to the right forever, x going to infinity. The y's are trying to come in for a landing, and they never quite get to 0, do they? Because the asymptote. But what's a limit? Is a limit where you get to? What you get to, I should say? No. A limit is what do you approach? Even though you never get there, you eventually get so close, you might as well just say, I'm heading to 0. That is 0. Oh, when you circle a 0, Mr. Wade's class, you get a donut. Let's put some sprinkles on there. Okay, that's ridiculous, I know. If anybody out there is making another connection, Mr. Wade, when we do an infinite limit, the only time we get an answer is when there's a horizontal asymptote. Yes, infinite limits and horizontal asymptotes are pretty much the same thing. Okay, we're going to do some horizontal asymptotes in this chapter. All right, the last one has a horizontal asymptote. Oh, that means we'll probably get an answer, at least if we go that way. As x approaches infinity, so it's going off to the right forever, isn't the graph trying to come down and get to 0 and it can't quite get to the horizontal asymptote? But isn't it going toward 0? So once again, that 0, hey, that's another donut down there. All right. Okay, now let's try letter D. And this time we're doing what's called a right-hand limit. Remember this from last time. We're going to approach 0, which is basically the y-axis. We're going to try to get to the y-axis from the plus side or the right-hand road. You're going to drive on the road from the right side, go towards the y-axis, see what happens the closer you get to it, okay? So again, I mean, this is the major theme today, the limits that you can do graphically. The other theme was for the conjugate, of course. But this theme is, can you just graph it? It's the same 4 graphs. Okay, so obviously, yes, we can graph it. So, oh, I left a red circle up there, just realized. Oops, okay. My magic powers didn't quite work there. So, as x approaches 0 from the right-hand road, you're going to drive on this road. The closer the road gets to 0, the y-axis, the more the y's are forced downward to negative infinity. Okay? So again, it's a little like an end behavior there, except that's only when you're approaching infinity and negative infinity. But it's kind of that concept. You see how it forces the arrow downward, right? Okay, approach 0 from the right-hand side. So we're going to come from the right-hand side. We're going to be on e to the x. Picture the growth curve. As you drive along this road from the right-hand side, the closer you get to 0, the more the road gets to y equals 1. You could actually, since it's a closed circle and not an asymptote this time, you could actually drive the car right up to the closed circle, park right on top of it, and say, hey, did I get to 0 from the right-hand side? Yep, you got there. Well, where's my y coordinate? I'm at 1 foot above sea level. That's actually one where you could just take 0 and plug it in and just do e to the 0 is 1. I mean, really, so that's like a super easy one right there. Again, though, doesn't matter if that's an open circle or a closed circle, the limit is the same because you're still going to it, right? Same thing over here. 0 from the right-hand side, so you have to be on the right-hand road, not the left-hand road. If you're over here, as you drive towards x equals 0 and you eventually park your car right on top of that dot, your y is currently 1. So that's another just plug in, basically, okay? And then the hyperbola case. As you approach 0 from the, not the left road, but the right road. If you're on the right road way down there that's hard for me to reach, what's going to happen? The closer you get to 0 on the right-hand road, the closer I get to 0, the y-axis, the more it forces the road upward. You know where I'm going? Infinity. So that's going to positive infinity. That's a horrible infinity there. Okay? So again, just looking at the graph. All right. Okay, let's do magic. All right. Now we have letter E. Oh, now we're approaching 0 from both sides, not plus, not minus. So these are the so-called two-sided limits we've done before. Okay. Again, they're the same pictures. If you know the graph, just draw it or just picture it in your head, and it's so much easier, right? A good visual. I love visual learning myself. A lot of you are like that. So, as you approach 0 from both sides now, picture the natural log graph. Uh-oh, there's something really weird we've never seen before until now. There aren't both roads. There's a right-hand road, but there's not a left-hand road. Remember, the natural log of a negative number does not exist. There's like an ocean out here, okay? Here's the road, here's the coastline, here's the beach. This is the water. You can't drive on the water, okay? So there's no road out here. You cannot physically approach 0 from both sides on a natural log graph. That is DNE does not exist. How about that? That is possible, okay? You have to have both sides to be able to pull off a two-sided limit. Okay, now this one we can do. As you approach 0 from both sides, you're going to go like this. You're going to 0 in. The closer the road gets to x equals 0, the more the y's are zeroing in on 1, kind of like the one before. They agree from both sides. It's even a closed circle on top of that, not that that mattered, but that's like as much of a limit as you could possibly get with no tricks. Guess what happens on this one when you approach 0 from both sides? The y's, the feet above sea level, are converging to 1. Also, again, just like before. And then the last crazy case. Now, unlike natural log, the hyperbola does have roads on both sides. The closer I get to 0, the right-hand road's going like this. The left-hand road's going like this. Those cars are never going to meet each other. They're going like opposite directions. You never meet. You do not agree from both sides. Now, if they both had gone up together like this, by the way, there is a graph we have drawn before that is, we kind of call it the volcano, like this. That's 1 over x squared. 1 over x to the 4th, 1 over x to the 6th, 1 over x to the even looks like a volcano. Then you could have said they were agreeing at infinity from both sides. But in this case, they disagree. They do not converge to the same place. So it's another does not exist. Okay? Heads up for the future. I'm eventually going to give you a 1 over x squared volcano. And you would have said, oh, the closer I get to 0, both roads are going to infinity. Even though they don't touch, they're both going to infinity. That's for the future, all right? Okay, let's flip it over to the back page. And we see a great example of what could come up in high school, college, whatever. So remember, we're doing limits, right? The very first thing you think of is, can I graph this? We just did a whole bunch of graphs and it was so easy, right? Yeah, that's not exactly in our wheelhouse right there, right? That's not one of the 9 major things we can graph all the time. So, if you can't graph it, what's the next thing we always say? Take the thing you're approaching and just plug it in. Now, that's kind of counterintuitive, right? Because you're probably thinking, Mr. Wade, if that's a number, I can plug it in. We've never plugged in an infinity before. We haven't. Not in AB, we haven't. So guess what? Even if it's infinity, you can kind of plug it in almost like it's a number. And let's see if you can get away with it. Now, guess what? We've talked about this before. If you get 0 over 0 or infinity over infinity, guess what? You're in the indeterminate world and you can't get an answer, so we've got to find some other clever algebraic means, right? Okay, so step 1, can't graph it. Step 2, try to plug it in and see if it is determinate. That's how you do every limit, those first 2 steps. Guess what? You can do this limit. You actually can do this. Based on earlier when we had those
Indeterminate conversations.
Thank goodness we had those indeterminate conversations earlier, because guess what? Isn't any number out of infinity 0? Okay, this is the 3rd level right here. Guess what? 3 things. Everything in calculus comes in 3s. Can I do the limit graphically? Can I just draw a picture? Remember, that's the first thing you do, right? What if it's too complicated to graph? Can I do it algebraically? Factoring, conjugates, other tricks I'm going to teach you, right? Can you do algebra to get out of it? Not in this problem, you can't, no. 3rd thing, can you do it conceptually? So you will do all 3 of these limits. Conceptually is basically conceptualizing that I got 1 out of infinite test problems right. Well, 1 out of infinity means I got a 0. Now put the negative on it. Well, negative 0, we all know there's no such thing. Negative 0 is just 0, right? So basically, you just got e to the 0. This is purely conceptual, not graphical, not algebraic. E to the 0 is 1. Everybody see that? So didn't this collapse and become a tiny number, smaller, 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 kind of like you're going to a horizontal asymptote, smaller, smaller, converging almost to 0, but e to the 0 is pretty much 1. But then 1 out of infinity test questions is 0. Oh, we got to donut again. The final answer is 0. Now, you don't have to know what that means today, but you simply know that the answer is 0. Although I can go ahead and tell you what it is. Didn't we say if you get a limit when you go to infinity? The only way you could have a limit, which is another word for a boundary as you go to infinity, is if there's a horizontal asymptote. Isn't 0 the x-axis? So who knows what this crazy graph looks like, but guess what? It's got a boundary on the x-axis called a horizontal asymptote. And apparently, the closer I go to positive infinity, the more it tries to land the plane at 0. There you go. So you're actually finding horizontal asymptotes. Okay? We'll do that more next time, but I just want you to focus on the fact that it's 0. Okay, last problem, letter G. And I know what you're all thinking at home. You're thinking, Mr. Wade, this is like a college level class. Challenge us. All right, if you insist. Okay, I'll give you a little bit of a challenge here, but it really isn't that bad at all. So we're going to approach 0 from the plus side. Step 1, can you graph it? Not the whole thing. I mean, it's like a hyperbola plus a natural log. Who knows what that looks like? Really weird, okay? So I can't quite graph that one, but wait a minute. Maybe I could. What if you treated this like 2 separate problems? Now let's think about the 3 major components of calculus. Bing, bing, bing. Remember derivatives? I need like a sound effect there. Derivatives, if you have addition or subtraction, you can do each derivative one at a time. Not if you have multiplication division. That gets into like product rule, quotient rule, right? If you have integration, the second major part of calculus, can you integrate 2 separate things with addition, subtraction, and just do like each one like it's its own problem? Yeah, you can, but not with multiplication division, right? In limits, the third major component of calculus, guess what? You can do the limit of this one, and you can do the limit of that one, and then just add your answers together. So actually treat this separately. It's not that bad, right? Now, this is a conversation for another day, but only in limit world. If it's multiplication or division, you can still do each limit and then just multiply or divide the results. That would never happen in derivative integration. It actually happens for limits. You can literally do like every little piece of the problem with a limit and then just throw it all together. Crazy, right? But that's another topic for another day. Limit as x approaches 0 from the right side of negative 10 over x to the 5th. Plus sign comes down, and then we'll do a totally separate limit as x approaches 0 from the plus side of 3 natural log of x. 2 separate problems. I bet you're already less intimidated, right? Okay, we do know these graphs. Thou shalt know thy graphs. So step 1, can I just graph it? All right, x to the 5th, odd. Isn't that a hyperbola? Mr. Wade threw a twist in there. It's a negative 10. It's a negative hyperbola. It's not a volcano because that's not an even power, right? It's an odd power. So, but it's a negative hyperbola, the standard diagonal hyperbola, but now it's diagonal this way. The negative 10 actually flips it the other way, okay? So it's a flipped hyperbola. That's a good thing to know, not a volcano. We're not going to do volcanoes today. Plus, and then I'll do this one. Oh, that's just that old tired 3 natural log of x. It's just a natural log of x graph. Who cares about the 3? It's just one of these things, and then the asymptote, vertical asymptote. Okay, let's see if we can get the answer now. This is the most advanced one of the day, but it's not that bad. As I approach 0, which is the y-axis, from the right-hand road, the closer the road on the right-hand side gets to the y-axis, the more it's forced downward to negative infinity. Plus, the second graph, the closer you get to 0 from the right-hand road, which it does have a right-hand road, not a left-hand, the closer you get to 0, the more the y's go to also negative infinity. Now you got to sit back and think, is this determinate or is this indeterminate based on the conversations we had today? Don't we all know that plus minus in a math class makes subtraction? Plus minus is a negative, right? This is negative infinity minus infinity. Let's think earlier. Was that determinate or indeterminate? That is determinate. Take away infinite dollars, and then I lost infinite more dollars. I have a gambling problem, I guess. I just lost infinity dollars. The final answer is negative infinity just because you knew your 2 graphs and you split it up. What if that had said negative infinity plus infinity? That would have been a problem. Isn't negative infinity plus infinity the same thing as, let's put the positive infinity first? Isn't that actually infinity minus infinity? So if you had a plus sign in the middle, that would have been indeterminate, because then you're thinking which infinity is stronger. I don't know. Even if you know it's a natural log, that's not enough information. So that would not have helped you. That would have been indeterminate, and that would have been a Calc 2 level question, so you would not see that in AB, all right? It can be done later in BC class. It can be done in Calc 2 in college, just not yet. So you won't see that kind of thing here, all right? Final answer, negative infinity. Ta-da! All right, go try 10-2, also 10-1, of course. Make sure you can kind of get a handle on how we do limits. And you're going to start getting really good instincts, and you will not be afraid of limits. Let me tell you what. I'll see you next time.
Hold it now.
You don't FOIL the part that are not. The part that is not, you idiot. As x approaches 0, the plane's trying to land and is trying to get down to, or did I just say 0? You stupid idiot. You still got a 0% on the test. Because while you may have gotten 1 billion...